Hello and welcome back, my dear students. So our lesson for today is the lines and planes in space. We need to learn how to find the equation of a line and equation of planes in the space with different cases. It depends on what's given, but we have usually a minimum requirement. So let me first, before we start in the three-dimensional space, I recall with you just how do we usually find the equation of lines in the two-dimensional space. So remember, when we need just to deal with lines in the two-dimensional space, we usually ask for 1 point, okay? We need usually 1 point on that line, which is, it could be like x1, y1, and we need slope. Remember, the slope, you can get it always as delta y over delta x, the change of y over the change of x. So the equation will be equals to y minus y1 equals mx minus x1. So this form is what we call the point slope form. This is the first case usually you see. So we need 1 point and slope in order to find the equation of the line. Or the second possible case, you may have 2 points given. So in case I have 2 points given as x1, y1 and x2, y2, we used to use the first point as our point. Okay, it's given, but I need to prepare for the slope. I need to calculate the slope. And the slope is equal to what? Delta y over delta x, the change in y over the change of x. And you can easily find it as y2 minus y1 over x2 minus x1. And once you have the slope and you have the point, you can easily use the same equation. If we need to simplify this equation and write it in this form, so this form is what we call as mx plus b. This form is what we call the slope-intercept form. Slope-intercept form. Okay, this is what you know about the two-dimensional space. So there's usually like a minimum requirement. So I need for a line point and slope. This is the minimum requirement. Or I could just have 2 points. Still, it takes me back to the first situation, which is I use the 2 points in order to find the slope. Now, what we'll be doing in the three-dimensional space, something similar to this. So we'll start the lesson has 2 parts. The first part is about lines, the second part about planes. So let's start about lines. So if I need to find the equation of a line in the three-dimensional space, see the idea now. What's the minimum requirement? What do I need to know? I need a point. So still it's the same as before. I need a point, and I need this point to be parallel to a position vector, A, which is A1, A2, A3. So see the minimum requirement? I need 1 point, this point, and I need a parallel position vector. Remember, we mean by position vector that we're starting from the initial point is at the origin. So I need 1 point and a parallel position vector. This is the minimum requirement. Okay, let's say I have this requirement. Why they are useful for me? So in case that I have 1 point, okay, and I need the equation for this line. Remember what's required? I need the equation of L, this line. Let's say that you have any other point on the line. In general, any general point, it could be like x, y, z. Okay. Now, since these two now are parallel to each other, remember the definition of parallel. If P1, this line, P1P, is parallel to the position vector A. So now I created a line. This is already L. We know 1 point on this line. This is the line we need to find, which we need to find its equation. And I assume another point on the line. I'll call it XYZ, PXYZ. This is parallel to the position vector A. Now, when we say parallel, remember, just this is a recall from before. What we covered before, we said that if you have 2 vectors parallel to each other, So we can write one vector as a scalar multiple of the other one. Let's just, because it's sometimes not showing as bold. So A can be written as scalar multiple of B. Same idea here, but we'll use the parameter T instead of C. So here I write the vector P1P equals T times the vector A position vector. So let's try just to use this definition about the parallel and just move forward. Okay, we know now this. From here we can continue. What's P1P? Remember always what we do just to find the position vector for P1P. It's terminal point minus initial point. Okay, so this is x minus x1. The second point is y minus y1, and then the third component is z minus c1 equals to, this is the parameter t, and a is a2, a3. Okay, now let's just distribute the t, multiply the t with by the vector. So now I have x minus x1, y minus y1, z minus z1 equals to a1t, a2t, a3t. Now since they are equals to each other, so that means the first component equals the first. This is equals to a1t, and the second equals to the second. Same thing applies to z. Okay, now if I need to solve these equations for x, y, z, okay, I need to solve it for x, y, z. So x will be equals to what? x1 plus a1t. And the second one will be y equals y2 plus a2t. And lastly, z equals z3 plus a3t. And these three equations are what we're going to call from now on the parametric equations. These are what we call parametric equations of the line. Okay, so these what we're going to call from now on as the parametric equations for the line. Okay, now this is how do we get these equations? How did we get them? So the idea basically, so minimum requirement, I need 1 point and 1 position vector, parallel position vector. Okay, so the equation would looks like x equals x1 plus a1t, y equals y2 plus a2t, and z equals z3 plus a3t. These are three equations. It's what we're gonna call from now on parametric equations. Okay, so these are the parametric equations. This is the first case, the minimum requirement that we may get. So minimum requirement, I have a point and a position vector, parallel position vector. So we got these equations, what we call the parametric equations. And then the other type of equations for the same equation, these ones, if I solve for t, notice that these equations, if I solve for t, solve these equations for t. So t equals to what from the first equation? It's x minus x1 over a. If you solve for t for the second equation, it's y minus y2 over a2. This is a1. And the third equation, it's z minus z3 over a3. Notice all of these t's are equals to each other, which means that these three equations equals to each other. So basically I have x minus x1 over a1 is equal to y minus y2 over a2, and this is also equal z minus z3 over a3. And these three are what we call symmetric equations. These are what we're gonna call from now on symmetric equations. So that means there's two ways to write the equation of the line in the plane, the equation of the line in the three-dimensional space. So either by using parametric equations or symmetric equations, which we can see as a summary here as our first case. Okay, now let's try one example on this case. So this is the first case on finding the equation of a line. See now this example. This is example 5.1. What does it say? It says just find equations for the line through the point 1, 5, 2 and parallel to the vector 4, 3, 7. And another requirement, we need to determine where the line intersects the YZ plane. Okay. So the first thing, what I need you always to do with these questions, try just to see what's given. So you have a point. So this point is basically acts as x1, y1, z1. And we have the vector, which is supposed to be a1, a2, a3. You see? I just classify the point as, or label the point as x1, y1, z1. And the vector a1, a2, a3. Okay. Now remember from the previous slide, what was the equation equals to? X equals x1 plus a1 t. Same applies for the three of them. We'll try to follow that. So it's very easy, straightforward. So I need to find first the parametric equations. Parametric equations. Okay. Let's find the parametric equations. So the parametric equations are x equals x1 is 1 plus 4t. You see? Simple. Y equals y1 plus a2t. Z equal the third one 2 plus 7t. Very simple. Directly. And we need to find the synthetic equations, symmetric equations. So for the symmetric equations, so basically what you need to do with the symmetric equation, you need to solve these equations for t. So the first equation will be x minus 1 divided by 4 equals to y minus 5 divided by 3, and this is equals z minus 2 divided by 7. And this is basically what we call the symmetric equations. Okay, very simple, straightforward. Now the second part of the question, they want us to determine where this line. Okay, remember this in the end, this is an equation of a line. So we need to find where this line intersects the YZ plane. So notice that if I need to find the intersection with the YZ plane, so that means I need to let x be equals to 0. That's all. So what I have to do is just to let x equals to 0. Okay, let's continue this question on the next slide. So here I need to continue by finding what? The intersection with the YZ plane, where x equals to 0. Basically, well, this is what I need to do. I let x equals to 0. Okay. So the three equations that we had already in the previous slide were x equals 1 plus 4t and y equals 5 plus 3t and z equals 2 plus 7t. Now if x is equals to 0, this is equals 1 plus 4t, and this can help me to solve for t. So this implies, so let's solve for t. So t is equal to negative 1 over 4. Now once you have the value for t, I'm going just to replace this value in the equations of y and z. So I have to substitute this value, substitute t in the equations of y and z. Okay, let's do that. So in this equation, now y equals 5 plus 3. Now t equals -1/4, which means that y equals 17/4. Okay, perfect. And I'll do the same for z. Equals 2 plus 7. T is -1/4. And this is equals 1/4. So hence, the point of intersection, the point of intersection is, remember we need to write them in order, x, y, z. So x is basically 0, y is 17/4, and z is 1/4. This is the point of intersection, and we're done. Okay, so if I need to find, let's say, assume the question is the intersection with the xz plane. So you let y equals to 0. Same thing. Any plane out of these three equals to 0, so it helps you to find t, and then you replace this t in the other two variables, x or y or z. It depends on the question. Okay. Now let's move to something else. So for now, the first part of the lesson, we know that we need to find the equation of the line in the three-dimensional space. What's the minimum requirement? I need minimum 1 point and a parallel position vector. 1 point, parallel position vector. Let's see another case. What could be given and what can we do? The second case that we may see, that instead of giving me like 1 point and parallel vector, they will give me 2 points. You see, just similar to the case of the two-dimensional space. If I'm given 2 points, then what do I have to do? If the question gave me 2 points, from the 2 points, I can use them to find a parallel position vector. Okay, the position vector PQ. How do we find it? Terminal minus initial. So this is the position vector for these 2 points. Okay, and this is what I'm going to use as this position vector. I'll use it as A1, A2, A3. Fine. Now we have the position vector and we have 1 point. You could use any of them, by the way, but usually we use the first one, P. And now I have 1 point and I have A1, A2, A3, and then I'll use just exactly like case 1, what we've done in the first case. Always, all of the coming cases, they always takes you back to case 1. Fine. Okay, let's try one example. So I need to find the equations for the line passing through the points P1, 2, -1 and Q5, -3, 4. Okay, so we have PQ. So this is the second case. What can I do in this case? So I need, so what's given here? So I have given 2 points. I need to find, let's use the first point as a point. So given a point, the first point, which is P1, 2, -1. This one, I'm going to use it as x1, y1, z1. Okay, this is the point. Now, what do I need to find? I need to find a parallel vector, a parallel position vector. So to find a parallel position vector. How do we find the parallel position vector? I'll use PQ. And this vector is basically what? Remember, we always take terminal minus initial. So PQ will be 4, -5, and 5. I subtracted the components of Q minus P. So this is this vector. And this for us, we're gonna use it as what? As A1, A2, A3. Now we have whatever we need. Now I'll use again case 1. So what do we need to find? We need to find the parametric equations. The parametric equations. Okay. What are the parametric equations? Very simple. We start with x equals, we take the x, 1 plus 4t. Y equals the second component, 2 minus 5t. And z equals negative 1 plus 5t. Okay, I need also the symmetric equations. Usually the questions specify, find symmetric and parallel. Symmetric equations will be equals to what? Just use the above 3 equations, but solve for t. No need to write t, just only solve for t. So this is x minus 1 over 4 equals y minus 2 divided by negative 5. And this is equals z plus 1 divided by 5. And these are the symmetric equations. Okay, so this is case number 2. I'm given 2 points. So now we know if I have 2 points, what's the plan? 1 point, okay, I use it as a point. Remember, we're trying to get the minimum requirement, which are 1 point and parallel position vector. I'll use the 2 points, okay, to find a parallel position vector. Just by only doing terminal point minus initial point, I'll get that vector. Now you have the vector, you have 1 point, and then go back to the to case 1. Fine. Let's see what do we have next. Now we have this definition, which is really helpful. It's gonna help us a lot in the remaining cases. So they tell me here that if I have 2 lines, okay, in the 3-dimensional space, and these 2 lines, they have parallel vectors A and B for each one of them. Remember, we usually for each line we see a parallel vector. So if these 2 lines L1, L2, they have parallel vectors A and B, and theta is the angle between A and B. These are the lines and these are the corresponding vectors which are parallel. So what's this definition is saying? That the lines L1 and L2 are parallel whenever A and B are parallel, which means that the behavior of the vectors and the lines, they have the same behavior. If the 2 lines parallel, then their parallel vectors again are parallel to each other. If the 2 lines, they have any intersection between them, so the angle between L1 and L2, okay, is theta. Let's define the angle in between as theta. And the lines L1 and L2 are orthogonal to each other whenever A and B are orthogonal. So basically that means they have the same behavior. Fine. So what's the advantage of this theorem? The definition. The advantage of this definition, that instead of dealing with lines and studying lines, I can study their vectors, their parallel vectors. Okay, remember each line we define it by 1 point and a parallel vector. So now instead of studying lines, I'm gonna study their parallel vectors. And whatever any conclusion I get about the vectors, I just reflect it for the lines. So if I check the 2 vectors parallel, so I can say that the 2 lines parallel. If I check the 2 vectors orthogonal, then the 2 lines are orthogonal to each other. Okay, this is the idea. Now let's move to what do we have next. Now we'll move to the third case. So what does the third case say? We need to find the equation of a line given a point and a parallel line. So you see now what's given? I have a point and a parallel line. Now what we're going to do, It's a parallel line. I need the parallel vector from the line. Okay, I'll take the vector from the line. So I use the parallel vector as a1, a2, a3, and I continue just exactly like case 1. I'll continue like case 1. Okay, let's see what can we do in this question. See now what do we have? This is one. Now I'm trying just to include these cases are from the recommended questions. This is question number 5. What do we need to do? See, question here, it's asked you to find the parametric equations and symmetric equations for these lines. Now this question says what? The line, we need to find these equations for the line through the point 1, 2, 1 and parallel to, see, and this is, we have the point, this is will be for us x1, y1, z1, and they tell us that it's parallel to this line. Now remember, what do we need? We need a point which is already given, but from the parallel line, I can get what? The parallel vector. This is what I'm going to do. So what I have to do is to use the parallel line to get the parallel vector. How do we get the vector from the line? We always take the coefficient of t. This is basically the vector. So the vector v now for us will be equals to what? Or let's call it a. So a is equal to the first component, the coefficient of t is -3. Second, there's no t, so it's 0. The third equation, it's 1. So this is the parallel vector. This one for us, we know it as a1, a2, a3. Okay, now we have everything we need. Just go back to case number 1. So what are the parametric equations? So again, the parametric equations, we'll start with, this is the point, this is the a. So parametric equations, x equals 1 minus 3t, y equals 2, it's 0, so it's only 2, z equals 1 plus 1t. These are the 3 equations as parametric equations. Now I need to find also symmetric equations. Symmetric equations. Okay, I need to solve for t. Now notice the middle one has no t. Now I'll do the one with t, and then I'll tell you what to do with this one without t. So for x, it's x minus 1 over -3. This is equals to z minus 1 over 1. There's nothing here. Now what to do with the one without t? We just have a comma and we write it as it is. Y equals to 2. Okay? No need just to simplify or anything. I kept it just the same. But for the third one without t, I just had a comma and I wrote it as it is. Fine. So this is now we have case number 3. We know now 3 cases. So we'll move to the last case here. The last case, case number 4, it just, I need to find the equation, okay? The equation of a line given a point and it's perpendicular to 2 vectors. Okay, we have one point given and they told me that this point is perpendicular to 2 vectors. Let's say call them A and B. Now see the idea, what we're going to use. As I told you before, we're going to use this idea again. This is what we took in the cross product. So these are the 2 vectors, A and B. And I have this line, this is what the one we need to find its equation, L. This line is perpendicular on both of these 2 vectors. Now I'll use the idea of the cross product. So the cross product, what do we know about the cross product, the relation between the cross product and A and B? It's perpendicular on both. So it creates basically an angle of 90 with A and an angle of 90 with B. So this is perpendicular on both. If this is perpendicular on A and B, so this is basically parallel to L, right? Think about L. If it's perpendicular on A and B, and A cross B is perpendicular on A and B, so what's the relation between L and A cross B? They are parallel to each other. So basically now I know that L is parallel to A cross B. Fine. So now what do we need to do? The first step we have to do is to find a perpendicular vector. From where do we get this perpendicular vector? I get it as their cross product. Okay, just simple. I'll find A cross B. Now we need to find the equation of the line. How? The point is always given. So we have the point already. Okay, and I need, this is the required line L, is parallel to the vector A cross B. Remember the minimum requirement. We need one point, which is already here. This is the one point. And we need a parallel vector. So now we know that this L is parallel to their cross product. So now I can use their cross product as the position, the parallel position vector. And then we can proceed using case 1. Okay, so anytime you see the word perpendicular, remember you need to do what? Use the cross product. So this is the last case about the equation of a line. Okay, see now the example. This is again from the recommended questions. We need to find, same thing, parametric and symmetric equations for the line passing through the point 2, 0, 1 and perpendicular to two vectors. And they give us the two vectors. These are like A and B. Now this is the point as x1, y1, z1. Okay, we have the point. Now I need to find their cross product to have a parallel vector. So I need the first vector, let's call it, let's say that A is equal to the first one, and it's called B, the second one, 0, 2, 1. I need their cross product to act as our parallel vector. Remember, how do we find the cross product? First line is basically first row, I, J, K, and then we write them in order, 1, 0, 2, 0, 2, 1. If you try to find the determinant for this matrix, so this one will be equals to -4, -1, 2. You can check this out by yourself. So this is what the position vector is equal to. So now this is the position vector and we have the point. Now we go back to use case number 1. You see, every time we have to go back to case number 1. This is for us like A1, A2, A3, which is parallel. So our line L is parallel to this vector. So we have our line, let's say that we need to find the line, call it L. So L is parallel to A cross B. And we have the point. So what should be the parametric equations? Let's write them here. So parametric equations are, so the parametric equations, we write them down as, this is the point, so I have x equals 2 -4t, y equals again only -t, and z equals to 1 + 2t. Okay, we need again to find symmetric equations. Don't always forget that there's two requirements. This is, let's say, part A. Part B is the symmetric equations. And basically we get always the symmetric equations using the parametric equations just by only solve for t. So there's no t, it will be cancelled out. X - 2 divided by 4, and the second one will be equals t equals -y, and the third equation z - 1 over 2. This is the symmetric equations. Okay, and this is the last case about lines. So now let's just do a quick review of the 4 cases that we had. So the first case, which is usually the minimum requirement, case 1. So case 1 is basically the minimum requirement, which is what? I need a point and a parallel position vector. Point, parallel vector. This is the minimum. So we have parametric symmetric equations. The second possible case that we may see that they give us 2 points. In case we have 2 points given, then we need to prepare. Remember the target. 1 point, 1 parallel vector. So I use the 1 point which is already given. This is the 1 point already given. And then from these 2 points, I will create a position vector just by doing what? PQ, which is terminal point minus initial point. And then we go back to use case 1. Now we have point and parallel vector. The third case we saw, it's just if we have 1 point, notice they are the common always between them. All of them, they have 1 point given. They are always play around with the vector. And we have 1 point and a parallel line. If I have a parallel line, I'll use the equation from the parallel line to get a parallel vector. Remember always the coefficient of t is what actually the vector. So if I have the equation of the line, always the coefficient of t is the vector. So what I did here, just I used the equation of the line, I used the coefficient for t as the parallel vector. Now we have point, we have vector, we go back to case number 1. And the last case, if we have 1 point and it's perpendicular to 2 vectors. So anytime I see that there's a perpendicular to 2 vectors, I'll use their cross product. Because as you know, just the cross product is perpendicular on both A and B. And it will be parallel to L in that case. Okay, so now we have the cross product as the parallel vector. And the point is already given. Every time the point is already given for you. Okay, this is basically the 4 possible cases dealing with equation of a line in space. Okay, now we have, after we discuss all of the 4 cases to find the equation of a line, we have now a new concept, a bit different than what you know just from the 2-dimensional space. So in the 2-dimensional space, when we say that there's 2 lines parallel to each other, so we mean that they will never meet, okay? They will never meet whatever you extend them. So you extend the lines, they will never meet. And we know that their slope are equals to each other. They have similar slope. This is if they are parallel to each other. If they are not parallel, so we know the conclusion that they're gonna intersect. Okay, by default, because the definition of parallel that they will never intersect. So if they are not parallel, they're gonna intersect. So this fact in the 3-dimensional space, it's not true, because we may see a case of 2 lines that they are not parallel to each other and also they don't intersect. They are not parallel and they don't intersect. Basically, these 2 lines, they're gonna be in 2 different planes. Okay, so as you see, like L1, L2, clearly they are not parallel to each other and they will never intersect because they are already in 2 different planes. In that case, if it's not parallel, they don't intersect, we call them skew lines. So there's a name for this case, what they call it, skew lines. Okay. Let's see the next example. What do we need to show? So they tell me, they give me 2 lines, okay? And they ask me to show that these 2 lines are not parallel, yet they don't intersect. So basically, just like they asked me to show that they are skew lines, okay? So just like they are asking me to show that they are skew lines. Now, how can we do that? The idea to show that lines are skew, that means I need to show that they are not parallel to each other, and I need to show that they don't intersect. The first part is the easy one. I need to show that they are not parallel to each other. Okay, how do we show usually that 2 lines are parallel to each other? Let's go back there. So if they are parallel to each other, remember the definition. If I have the 2 lines, from the 2 lines I can get the 2 vectors. So the two vectors for A1, let's say for the first line, let's call it A for the first line. This equals to A1, A2, A3. And for the second line, let's call it B. So this is B1, B2, B3. So if the two lines are parallel to each other, we should have the same ratio between them. If they are parallel, so I have B1 divided by A1 is equal to B2 over A2, and this is equals to B3 over A3. This is the case if they are parallel to each other. So if I need to show that they are not parallel, so I need to do what? I need to show that they are not equal to each other. Okay, let's see. So what I'm going to do here as well as what I will start with the parallel. I'll show that they are parallel or not. So let's see if they are parallel or not. Okay, let's check what can we do. Again, remember from the definition that I'm dealing with lines, but it's easier to deal with vectors rather than lines. So I'll find their corresponding vector, the parallel vector. So for the first line, okay, for the first line, I'll just find the first vector. Okay, so I'll call it, let's say, call it V1. The first vector from the first line. We always take what? The coefficient of t. So for the first one, it's -1, and then 2 and 2. V2 will be equals to what? From the second one, it's the coefficient of s this time, they called it. The parameter is now s instead of t. So this is 1, -1, and 3. Remember, we always take it if x is equal to. So they don't have to be on the same side. X or y or z equal to. Okay, so this is V1, this is V2. Now I need to show if they are parallel or not. I'll need to find the ratios. I need to check the ratios. Okay, let's see. So I have 1 over -1. Is it equal to -1 over 2? Is it equal to 3 over 2? Are these equals to each other? Clearly they are not. So it's not parallel. They are not parallel. Okay, so it seems the first condition to be skew is satisfied. They are not parallel. Now the second idea, how do I show that these lines, they have intersection point? Now the idea to show that they do intersect or they don't, what they do is they assume that they intersect. See the idea? We assume that they do intersect. If we assume that they do intersect, so this is for the intersection. We assume that they intersect. Assume that they do intersect. If we assume that they intersect, so basically I have x1 equals x2 and y1 equals y2 if they do intersect. I'll use these two to find what's s equals to, what t equals to. And then I'll substitute these values for x and t. I'll substitute them where? In z1 and z2. I replace s and t in z1, z2. If I have z1 equals to z2, then my assumption is correct. They do intersect. If I get z1 does not equal to z2, so this is a contradiction. So my original assumption was wrong. Okay, so you see, this is what they call, they do the proof by using the contradiction idea. So, okay, I need to show they intersect or not. Assume yes, okay? If they do, then x1 equal x2, y1 equal y2. These two equations will allow me to find the values for s and t. And then if I replace, if yes, they do intersect. So if I replace the values for s and t in z1 and z2, they should give a true statement. If they are equals to each other, so yes, they do intersect. If not, then my original assumption was wrong and they don't intersect. Okay, so this is the technique that we're gonna follow. Let's try in our question. So we did the parallel part. We need now to check for intersection. Do they intersect or not? Okay, so I'm continue solving the same question. So I need to check if they do intersect or not. If they intersect, then x1 equals x2, y1 equals y2, and z1 equals z2. Now I'll start with x1 equals x2. Okay, from the two original equations. So x1 is negative t plus 2. Oh, let's write it with negative t, I said. It's negative t. Let's write them down here again better. So I have x equals negative t plus 2, and y equals 2t plus 1, and z equals 2t plus 5. The second set of equations group of equations is x equals s plus 1, y equals negative s plus 2, and z equals 3s plus 1. I'm getting these equations from here, okay? They are the same equations, but I solve for x, y, z. Okay, now we said that I'll start with assuming that x1, the first one, is the same like the second one. Okay, let's do that. So x1 negative t plus 2 equals s plus 1. Okay, solve this equation for, let's say, for s. So s is equal to negative t plus 1. Okay, this is the first equation from x1 equals x2. Now I'll do y1 equals y2. This wise, let's say 1, 1, 1, 2, 2, 2. Okay, so this is 2t plus 1 equals negative s plus 2. Solve this again for s. So this is equals 1 minus 2t. Okay, now this is a system of equation. You can solve it any way you like. Substitution, elimination, use your calculator, do whatever you like. So by, let's say, elimination method. By elimination method, if you solve it, you'll get t equals to 0 and s equals to 1. Okay, great. Now what do I need to do? If t is equals to 0, s equals to 1, try now to substitute in. We need to check if z1 equals z2. Okay, let's try. Z1 equals to what? 2t plus 5. So this is 2, 0 plus 5, and this is equals to 5. Try z2. 3, what's s1 plus 1, and this is equals to 4. So clearly z1 does not equal to z2. They are not equals to each other. Okay, so that's mean our original assumption. So this is a contradiction. This is a contradiction for our original assumption. So that's mean hence the lines do not intersect. Don't intersect. So now what do we see? That they don't intersect, and if we go to the previous slide, and they are not parallel to each other. So if they don't intersect and they are not parallel to each other, so the two lines are Q lines. So the two lines are skew lines. So if any time I ask you to show whether the two lines are skew line or not, you need to check these two conditions. You have to check for parallel or not, easy, just only use the ratio, and you have to show whether they do intersect or not. Okay, let's try another example. Something like this. This is one of the recommended questions in your textbook. This question number 11. See, the question says what? We need to determine whether the lines are, this is usually the form of the question. Determine whether the lines are parallel, skew, or intersect. If they do intersect, find the point of intersection. Okay? Now we need to try. The first step always with these questions is to find their corresponding vector, right? I need to find the corresponding vector before I solve. So what's V1, which is corresponding to the first line? Remember, we always take the coefficient of t. So it's 1, 0, 2. The second vector V2 is basically for the second line. So it's 2, 2, 4. Okay? Now let's check if they are parallel or not. We'll start always with the parallel or not. I need to find the ratios. So it's 2 over 1. Is it equal to 2 over 0? Is it equal to 4 over 2? Notice they should be all equals to each other. These are not equals to each other. These are not equals to each other. So this is not parallel. It's not parallel. Okay. Now I need to check if it's intersected or not. I need to check for intersection. Okay, assume yes. Assume that they do intersect. If they do intersect, then what will happen? x1 equals x2. So I can start that 4 plus t equals 2 plus 2s. Okay? Solve this equation for whatever you like, for t, for s. This time it looks easier for t. So this implies that t equals 2s, okay, minus 2. So this is the first equation. Now I'll take the second two equations, y1 equal y2. So it's 2 equals 2s, which basically means that s is equal to 1. Great. Now if I substitute this s equals to 1 in this equation, so I'll get t equals to 0. Now these are the two values that I got for s and t. Now remember, since we assumed that they are parallel to each other, so I have to check for z. Check whether z1 equals to z2 or not. Okay, let's check z1. z1, this is with t. So this is a 3 plus 2 times 0, and this is equals to 3. Check z2. This one with the s. It's negative 1 plus 4 times 1, and this is again equals to 3. Oh, they are equals to each other. So z1 equals to z2. Yes, so they do intersect. Yes, they intersect. Now you need to find the point of intersection. The point of intersection. Now the point of intersection, how do we find it? Remember, if the two lines intersect, then the point should be in common for both of them. So either you replace t in the first group of equations, the first group of parametric equations, or you replace s in the second one. Whatever you decide to use, you should get the same point. So I'll substitute t equals to 0 in the first group of parametric equations. Okay, if t is equals to 0, so then x will be equals to 4, y equals to 2, and z equals to 3. This is supposed to be the point of intersection. Okay, so if you try, let's say you didn't like to use t, you used s in the second group of equations, you'll get exactly the same result. Fine. So are the two lines skew lines? No. Are they parallel? No. But they do intersect. Hopefully all is clear so far. So now we're done with the first part of the lesson. So we discussed 4 cases of the equation of a line, and we took one extra definition about the skew lines, and we checked two examples about skew lines or not, and we found the intersection point. Now we'll move, after dealing with lines, we'll move to equation of plane this time. This time I need the equation of plane, not only line. So for the equation of plane, we need always to start with the minimum requirement. You see, they follow the same pattern. So I need the minimum requirement to find the equation of plane. What's minimum required? So a plane in space is determined by specifying a non-zero vector. Okay, so we have a non-zero vector, which is this one. This is the plane, the blue one. A non-zero vector A, which is A1, A2, A3, that is normal to the plane. Okay, and a point lying in the plane. So same thing, I'm still having a point, but I need not only one point, and I need a normal vector. What do we mean by normal? Usually they use the word normal, that is perpendicular, that creates an angle of 90 degrees. So this vector here, A, creates an angle of 90 with the plane. They call it normal vector. So you see, unlike the equation of a line, here I need one point and one normal vector. If I have one point and one normal vector, so let's say that in that plane I have one point P, choose any other point, call it P in general. So I have now the vector P1P. If it's perpendicular, between the relation between them, they are perpendicular to each other, which means that their dot product equals to 0. Remember, how do we translate the perpendicular vectors? We say that their dot product equals to 0. Okay, so I have these two vectors and their dot product equals to 0. Let's try to do the calculation for the dot product. So the first vector is P1P. We did it normally. This is P1 as x1, y1, z1. P is x, y, z. So P1P will be what? X minus x1, y minus y1, z minus z1. Just only terminal minus initial. Do the dot product. Remember how we usually do the dot product. First component times the first, plus second times the second, plus third times the third. And this is what we get. And this is now the general form of the equation of a line. It looks like this. So we have the normal vector where we use it for A1, A2, and A3, and the given point as x1, y1, z1. Fine. So this is case number 1 for us. This is the first case, the minimum requirement. Now let's try to solve this question. What do we have? I prepared already the equation in front of you. So I need to find an equation of the plane containing the point, a point 1, 2, 3. So this is basically for us x1, y1, z1. Okay, it's good to label them always. It's easier to follow the definition. And it's a normal vector, which we use it as a1, a2, a3. Okay, and sketch the plane. They want us to sketch the plane after. Okay, this is the general form. I need to apply in this general form only. There's nothing else we can do. Very simple. So let's try to apply. So this is 0 equals a1 is 4, x minus x1 1 plus a2 5, y minus y1 is 2 plus a3 6, z minus z1 is 3. If I do simplify this equation, so it would be equals to 4x minus 4 plus 5y minus 10 plus 6z minus 18. Add the like term, so you'll get 4x plus 5y plus 6z minus 32 equals to 0. And this is basically the equation of the plane. Notice it has 3 variables, x, y, and z. Okay, so this is our first case, a straightforward, easy case. This is the minimum requirement. So remember, I always like you to remember the minimum requirement. So I need one point and a normal vector. Okay, let's see what do we have next. We need to sketch the plane for this question. So I have already a point and the normal vector. If I need to sketch the plane, basically what we need is, this is important just to think about this, what I'm just saying now. In the two-dimensional space, when we graph any line, remember what's minimum you need to graph any line. So to graph any line, we always need minimum 2 points, just to guarantee the uniqueness of that line. So with 2 points, you can't draw more than one line passing through these 2 points. If I have 1 point, I can draw infinitely many lines, so it doesn't work. So minimum, I need 2 points to guarantee the uniqueness of that line. When we're talking about planes, so how many points do I need minimum to guarantee this uniqueness of plane? I need 3 points. Okay, so it's unlike the line. With the plane, you need 3 points. So basically, when I need to sketch it, I need 3 points on that plane in order to graph it. And as usual, the easiest points to sketch are the intercepts. So I need to check the x, y, z intercept. Basically, that's it. We have the equation of the plane, remember? This is the equation of the plane. So I need the intercept. One time you let xz equals to 0. So you find the y-intercept, which is this one. And the other time you let x and y equals to 0. So you find the z-intercept. And lastly, you do it same thing for y and z 0. So you get x. So you always like cancel out 2 of them. You keep the third one. These are the intercepts. So I need the plane which contains these 3 points. So nothing else. That's it. You don't have just to be super professional in graphing. I need just the minimum. So what I need you to take out of this part about graphing, that to graph a unique plane, I need 3 points. Anything extra is good, but minimum I need 3 points. Fine? For the line, it's enough to get 2 points only. Now, if I solve this previous question, just the previous equation, I already did that, by the way. So this is this form. If I just simplify it, add the like terms, I get this form, which we did already. So the form in general is just ax plus by plus cz plus d equals to 0. Okay? Now, from this equation, if I need to go back, reverse, always we need to go back. So if I need to know the normal vector, what should be the normal vector in that case? If I need the normal vector, I'll take the coefficient of x, y, and z. So it should be the normal vector as a, b, c. Remember before with lines, what did we get? The coefficient of t. The coefficient for t were the parallel vector. While with the plane, we take the coefficient for x, y, z to get the normal vector. So it's always important to know that. Now, let's move to the second case. Let's review the first case, which we already did. This is the first case, which is the minimum requirement. 1 point and normal vector, this is the equation. Now, the second case, as expected, with lines, the second case was 2 points. With planes, I should have 3 points. Now, if we were given 3 points on a plane and they need me to find the equation of that plane, again, keep in mind always the minimum requirement, point and normal vector. The point is already given. We have always the point given. No need to worry about the point. The point is given. Already use P, for example. Now I need a normal vector, which is a perpendicular vector. So again, I'll use these 3 points in order to find another 2 vectors. I'll call them whatever you like. We need 2 vectors. Like I need to use PQ and QR, okay? I could just change the direction of the arrow. So this is PQ. This is PQ and QR. Their cross product will be what? Perpendicular on the, or normal on the plane. So now I have 1 point P and their cross product is normal on that plane. So this is the plan for this case, case number 2. If I'm given 3 points. See now, something like this. Again, I need to change the direction of the arrow. It's PQ. Okay, now find the plane containing the 3 points P, Q, R. Okay, so now what do I need to do in this case? I need to prepare. I need to find what's PQ as a vector. Remember always, how do we do it? We do terminal minus initial, Q minus P. So this is equals to 1 minus 3, 2. And I need to find QR. And this is again equals, I need to subtract R minus Q. So this is 1, 6, negative 6. Okay, once I have the two vectors, I need to find their cross product. PQ cross QR. And this is equals to, for the cross product, you need always the matrix. So I, J, K, and this is 1, negative 3, 2, 1, 6, negative 6. If you do the cross product, this will be equals to 6i plus 8j plus, I'll leave it as an exercise to do it yourself. And this is 6, 8, 9. Now what we're going to do, let's put it next to it better. So this is equals 6, 8, 9. Now as a conclusion, just let's check what do we have. We have 1 point and we have one normal vector. This vector is normal on the plane. So that's mean this point, I'm gonna use it as x1, y1, z1. And this is basically A1, A2, A3. Okay, now let's find the plane equation. The plane equation. What do we know about the plane equation? It looks like what? We know that I should do it as, we start always with the A. So this is 6x minus 1 plus A2, 8y minus 2 plus 9 z minus the third component is 2 equals to 0. If you expand and simplify, you'll get 6x plus 8y plus 9z minus 40 equals to 0. And this is the plane equation. Okay? Clear the case? So this is case number 2 in finding the equation of plane if given 3 points. So if I have 3 points, you need just to start. This needs more work, this question. You need to prepare for PQ, QR, and then you do the cross product. And then after that, you have 1 point, you have the cross product. Use it in order to find the equation of the plane. Fine. Let's see if there's any other cases. Usually I take 2 cases from your slides and 2 other cases from the problem solving, the recommended questions. Now again, this is similar to the definition that we saw before. So it says that if you have 2 planes and they are parallel to each other, so whenever their normal vectors are parallel and the planes are orthogonal, whenever their normal vectors are orthogonal. Same just like the definition before. So they have the same behavior. If I'm studying the 2 planes parallel, then their normal vectors parallel to each other. If the 2 planes perpendicular, then their normal vector again perpendicular to each other. That's it. Okay, let's see how can this be useful in our coming case. This is case number 3. So in case number 3, we're given a point and a parallel plane. It's a point and a parallel plane. Okay, and they give me the equation of the plane. What can we do? So it just seems like I have 1 point and you have a parallel plane. Okay, think about it this way. If I need to find the equation where I have this point. Okay, let's try to make them with the same. I need them to look a bit more like parallel to each other. This is the point P. And this is the plane which is parallel to the plane where I have this point P. Now I'll use this plane, the other one, in order, I'll take the A, B, C in order to get the normal vector. So this one will be a normal vector for this plane. If it's normal for this and these two are parallel, so this is normal for our plane also. Okay, so I'll use the same normal vector, which is this one is A, B, C. So this vector is perpendicular on this plane and it's perpendicular on our plane. So this is what I use as normal vector. So now I have a point and I have the plane. I can use case 1 directly. Fine, this is the idea in general. If the two planes parallel to each other, then the normal for the first one is normal for the other one. They have always the same relationship. Okay, see the question for case number 3. So the question says that I need to find an equation of the plane that passes through the point or has the point 1, 4, -5 and is parallel to the plane defined by 2x minus 5y plus 7z equals to 12. Okay, so directly I have the point. So this is for me directly as x1, y1, z1. You see, it's never been an issue with a point. It's always given. This is the point. Now this is parallel to this plane. So that means our plane, the one that we need, has the normal vector. Normal vector. What will be the normal vector? Remember, we take the coefficient for x, y, z, but under one condition. You need them all to be in one side, all of them. X, Y, Z, Z to be on one side altogether. So let's say if I give you the question like this, let's say, assume, I need just to trick you. So you have to send this to the other side before you use it directly. Okay, so they should be all in the same side. So now the normal vector should be 2, -5, 7. Okay, perfect. Now this normal vector will be normal on our plane. So this one I'll use it as A1, A2, A3. So now I have normal vector and I have a point. I can go back to the first case. So now the plane equation. What's the plane equation? It should be 2. We always start with these. X minus 1, x minus x1 plus, well, this time it's negative, -5 y minus 4 plus 7 z minus 5, so it's plus 5. This is all equals to 0. Try to simplify. You'll get 2x minus 5y plus 7z plus 53 equals to 0, and this is the plane equation. Okay, so you see, always all of the cases, they takes you back to the original case, the first case. Okay, now there's another question that you can try yourself. This one, this is one of the recommended questions. Say they tell you that the plane containing this point, which is x1, y1, z1, and it's parallel to the plane with this equation. So that means the normal vector should be what? It's already written down. So the normal vector should be -2, 4. There's no z, so it's 0. -2, 4, 0. And then you find the equation. That's it. This is question number 21. Now let's see if we have any last case. Case number 4. In case number 4, so you see the cases, usually the fundamental case, and then they use 2 points or 3 points, it depends, line or a plane. Case number 3 with parallel line or parallel vector, parallel plane, sorry. And case number 4, we have still a point, but perpendicular to 2 planes. Now see the idea here. I need the equation of the plane given a point, okay, and parallel to two other vectors. Parallel to two other vectors. That's good. Now, let's assume that the point is here. And this point is perpendicular on two other planes. Let's say that this is plane number 1 and this is plane number 2. So it's perpendicular on these two planes. Now, if I think about the normal vector for these planes, this blue vector is normal on P1 and the green one is normal on P2, and their cross product, right? These two vectors, let's call it V1, V2. Their cross product will be what? Will be normal on our target plane. Let's call our target plane as P in general. So I use this normal vector, their dot product will be perpendicular on our target plane. The target plane is the highlighted one, the floor. Okay, so now the plan is to do what? From the two given planes, we'll take their normal vectors and then I'll use their cross product to be normal on the floor, the base plane, the one highlighted. And now I have one point and I have a normal vector. I'll use again case number 1. So you see, every time we see the word perpendicular, we use the idea of cross product. Okay, let's see this example about this case. This is again from the recommended questions. I need to find the equation of the plane containing the point 1, 2, 4 and is perpendicular to two other planes. Okay, just exactly we'll do what we have to do. So the point is 1, 2, 1, which is basically x1, y1, z1. Okay, done with the point. Now I need normal vector number 1 for the first one. So for the first plane, P number 1, it's x plus y equals to 2. So the normal vector, let's get the normal vector. Let's call it v1 equals to the coefficient for x is 1, for y1, z is not there, 0. And from the second plane, which is 2x plus y minus z equals to 1, so the normal vector will be equals to what? v2 will be equals to 1, negative 1. So now what do we have? We have the point and we have two normal vectors. Now I need to find the normal on our plane, the one we need. So the normal vector on the required plane should be what? v1 cross v2 in the plane that we need to find its equation. So v1 it's I, j, k, v1 is 1, 1, 0, v2 is 2, 1, negative 1. We need to work with the finding the determinant for this matrix, and this one will be equals to negative 1, 1, negative 1. And this is basically a1, a2, a3. So now what do we have? We have the point and we have the normal vector. So what's left is only to find the equation of the line. So the equation of the line will be what? The plane equation, sorry. The plane equation is negative times x minus 1 plus, that's 1 only, y minus 2 minus 1 again z minus 1 equals to 0. You could simplify it as negative x plus y minus z equals to 0. And this is the plane equation. Okay, as you see, section 10.5 is really a heavy one, especially that I tried just to help you with adding new ideas which are already included in the recommended questions. Okay, there's few slides left. We've done with all of the 4 cases so far. Now there's this part here, which is about the to find the intersection between 2 planes. So if I have 2 planes and I need to find the intersection between them, basically, if you think of normal situation and you think about 2 planes, their intersection should be what? A line, right? Like the intersection of 2 lines. If I think about 2 lines and they do intersect, the intersection should be what? A point. If I think about the 2 planes and let's say that they do intersect, okay? Let's assume that they have intersection between them. The intersection should be what? A line. Okay. Now, to find the point of intersection between 2 lines, okay, what I have to do is one thing. To find the line of intersection for these 2 points. What we need to do here is okay, so let's say that I'll let one of the 3 variables, okay, I'll let one of the 3 variables to be t. So I'll let z equals to t. You could let any of them, where t is any real number, where t belongs to r. That's mean why I did that. I need you to understand usually why. Now I have 2 planes with the 3 variables, x, y, and z. In order to solve these 2 equations, I can't solve 3 variables if I'm given 2 equations. This is a fact you have to understand in math. If I need to find 2 variables, I need 2 equations. 3 variables, they should give me 3 equations, okay? If I'm given only 2, I'll assume that I know one of the 3. So I'll assume that z is equal to t, where t is the parameter, any real number. Okay, so I have to start with this. So assume that z equals to t. Now, I'll start with substitution. So if z is equal to t, then the first equation is x plus 2y plus t equals to 3, which means that x plus 2y equals 3 minus t. I'll do the same in the second equation. X minus 4y plus 3t equals to 5, which means that x minus 4y equals 5 minus 3t. Now I have this system. Remember, t is a constant for us. It's only a parameter. Now I have this system. If I solve this system, solve by, let's say, elimination method. By elimination method. How do I solve by elimination? I need to cancel either x or y. So maybe I can do, this is, let's say, equation number 1, and this is equation number 2. So I can subtract equation number 1 minus equation number 2. So what do I get if I subtract these 2 equations? So I'll have x plus 2y equals 3 minus t. And this is supposed to be minus x minus 4y equals 5 minus 3t. So if you subtract these 2 equations, you'll cancel x, and 2 negative 4, so this is 6y equals negative 2 plus 2t. Solve for y, so y is equal to negative 1 over 3 plus 1 over 3t. This is y. So now we have the second equation. Remember, in the end, your result, if think about the result as a straight line, so it should be 3 parametric equations. I need the equation of a line, and usually we write the line equation as a 3 parametric equations. Now I have z, I have y, I need to find x. So back substitution in which equation you like, in any equation, let's say equation 1. In equation 1. So now this is x plus, or let's write x equals to what? X equals 3 minus t minus 2y. And this is equal, x equals 3 minus t minus 2. Y is what? Negative 1 over 3 plus 1 over 3t. If you simplify this equation and add the like terms, so this is 11 over 3 minus 5 over 3t. And this is the equation for x. So the two planes, they do have intersection, and this is a line. The line of the intersection is a line, which I can write it as x equal the parametric equation. 11 over 3 minus 5 over 3t, y equals negative 1 over 3 plus 1 over 3t, and z equals to t. This is the equation of the line. Okay, this is their intersection, the intersection between these two lines. Okay. Now the last part in this note, we need to find, remember before we found the distance between point and a line. Point and a line. Here I need to find the distance between point and plane. So I have a point and I have a plane, and I need to find the distance. And we always, when we talk about the distance, we mean the shortest distance. That's why it's basically that we drop a column over this plane to find the distance. No need just to go through all of the proof, but basically I need just, this is a point on the plane. Okay, so they try to find, this is the point that we need to find, P naught. So they find another point on the plane, P1P. Okay, this is a vector P1P, and they try to find the projection, or we need the length, so it's as a component. So they find the component of P1P, this vector, along the normal vector A to find the distance, which is this distance here. So P1P naught is basically terminal minus initial, and I need it as the component. The distance is basically the component. So that's it, the same graph. This is the distance. So the vector P1P times, this is the rule for the component. You see, A dot B over the magnitude of B. So this is what I'm doing. So it's P1P naught dot A over the magnitude of A. If you replace all of that and you do all of the simplification, again, no need just to do the proof. You can use the formula directly. So the distance between a point and plane is basically this. Okay, this is the distance from a point into a plane. And the point for us is x naught, y naught, z naught. This is the point P naught. And this is the plane equation. As ax, you know the plane equation, it's ax plus by plus cz plus d equals to 0. So what I'm going to do is just like to find this distance. I need to replace, notice what I've done as the rule. I substitute the point in the equation of the plane, okay, with the absolute value, because I need a distance, it's supposed to be positive, divided by the magnitude, just like the magnitude, a squared plus b squared plus c squared. Okay, let's try to apply this in our last example. This question says what? We need, this is example 5.9. I need to find the distance between two parallel planes, okay, we were talking about one point and plane, and then suddenly we're talking about two planes. So what's the story? If I need the distance between two parallel planes, so it's still the same distance between one plane and one point and one plane. If they are parallel to each other, it's still the same distance, right? So this is the same distance we're talking about. So this is what I need to do. I need to find the distance between the parallel planes. Okay. What are the two parallel planes that I need to find their distance, the distance between them? I guess, do I have it there? I think it's not. Is it here? Okay, so maybe it's by mistake, it's not there. Anyway, I can add them. So the equations of the two planes are P1 as 2x minus 3y plus z equals to 6, and the second plane is 4x minus 6y plus 2z equals to 8. This is the question. These are the two planes. So now I need to do, it's up to you, take any point in plane number one. So the plan here, I need to take 1 point on P1. What should be the 1 point? You could take what? Let's say any point, any point. So you could take, for example, x, we could take x equals to 0 and y equals to 0. So if x equals to 0, y equals to 0, then the point will be what? Say 0, 0, 6. So this point for us, we can use it as, this is x1, y1, z1. Okay, now we have the point. So you can take any point, okay? But I just took these for easy calculation. I let two of them, like I found the intercept, any intercept, one of the three. Now I need to do what? The second step. So I have 1 point, just choose anything you like. And then I need to plug the point in plane number 2. So I use plane number 1 to get the point, then I'll plug this point into P2. So to get what? If I do that, so I'll have this is the rule of the distance. Let's follow it here. So D equals, I need to replace the point in P2. So this is 4. X1 now is 0 plus negative 6y is 0, okay, plus 2z, which is 2z is 6. Notice this equation should be all with d, so I need just to write it as what? 4x minus 6y plus 2z minus 8 equals to 0. I need to plug it here. So negative 8 with the absolute value. This is usually a common mistake, by the way. Remember always when you plug it in the numerator, it should be the equations be equals to 0. I have them all on one side. Divided by radical, this is a, b, c. So it's 4 squared plus negative 6 squared plus c is 2 squared. If you do the calculation here, it will be equals to 2 over radical 14. If I do the calculation and simplify, you have a calculator, you can do that easily. So the result will be equals to 2 over radical 14. Okay, that's all for section 10.5. It needs your practicing, studying. I'll add for you a summary for this section, which is important with all of the cases. It's good to review. This is an important section. And the next section and the last one in chapter 10 will be 10.6. See you till that time. Take care.